Hello, my name is JamesKnight, and this is my final project for ADTA 5560, Recurrent Neural Networks for Sequence Data. In the first part of the project, we were asked to find a time series dataset. A time series dataset is a type of series data where the data points are indexed in order of time. So I went to data.world and I was able to find a data set that lists the average temperature for every month between March 1855 all the way through September 2013 for the major territories of 7 different countries. And those countries include the US, Brazil, Russia, Canada, India, China, and Australia. So in total, there were 650,000 records about. So those are all temperature readings across those territories. And it was, like I said, it was the average temperature for every month. I did some exploration of the data set, and there were a few notable things that I found. One is that a lot of the readings, the temperature readings for months before 1891 are blank. So you may need to figure out how you want to handle those blank records if you're using this data set for any kind of machine learning or analytics. The second thing I found was that the format of the date switches between year dash month dash day and month slash day slash year. The data are ordered chronologically, so it may not be a problem if you're just using the data set as is. But if you were to want to join this data to a different data set, you would probably need to standardize the date format to get a good join. And if we look on the table on the slide, I just summarized some of the things I'd already talked about with the data set, such as the record count, and I laid out the features as well. There were a total of 5 different features in this data set. It was the date, that was when the temperature reading was taken, the average temperature, which is in Celsius, the average temperature uncertainty, which I believe is some kind of a t-score, and then the state, which in the United States they're called states, but they may be called something else in different countries, but that's the name of the field. And then the country. For the second part of the project, we were asked to generate a sine wave data set and try to predict some of the points using a simple recurrent neural network, or RNN. From the RNN model, I set up simple network with 2 layers, an RNN layer for learning the sequence data, and a fully connected layer for producing the final output. And the RNN layer contained 120 neurons, as you can see from the image on the left. I also zoomed in to one of the RNN neurons in the diagram to show you what the architecture of a simple RNN cell looks like. So starting from the left, you have the hidden state from the previous iteration, and then coming in from the bottom, you have the current input. So those two things are combined and processed through a hyperbolic tangent function, which produces the current hidden state and the output, which is often the same as the current hidden state. So my sine wave data consisted of 1,000 data points ranging from 0 to 50. I split the data for training and testing using 80% for training and 20% for testing. The model was trained in 5 epochs. As you can see by the chart on the left, we had a big dip after the second epoch, that's index 1, and then some spikes and dips, but ultimately we finished with a loss pretty close to 0. I should also mention that this loss is calculated with MSE. We used we used MSE for the loss function and Atom for the weight optimization function. The chart on the right shows the result of what happened when we predicted the 20% of the sine wave data that we held out during testing. So what you can see from here is that the test data, the actual values in blue, and the predicted values in orange were really close to one another, because we can see these two sine waves almost overlap, which seems to say that our model did a pretty good job at predicting the sine wave data. Part 3 of the project covered the concepts of long short-term memory, or LSTM. LSTM is a type of recurring neural network that improves on the simple RNN's main weakness, which is its short-term memory. If an RNN has to learn a very long sequence, it begins to forget information that occurred early on in the sequence, even if the information is relevant. The reason for that is because the hidden state of an RNN gets multiplied by a weight during the training process based on the loss. Eventually, that weight gets very close to 0, and when you multiply a number with 0, you get a very, very small number. The result is that the RNN's hidden state will stop updating, which means that the network stops learning. LSTM overcomes this short-term memory problem by introducing a new state called the cell state. The cell state can be thought of as an inner state for information. The cell state carries information through every timestamp in the training process without any unintentional loss of information. The reason for this is because the cell state does not get multiplied by any weights during the training process. The information in the cell state may change, but that's due to an intentional filtering process which is done by the gates, and we'll talk about the gates in the next slide. For now, we just need to understand that the cell state can carry all relevant information from all the way in the beginning to the very end of the network. The cell state can be viewed as a flow of information or as a snapshot in time as the state of the cell during that time, since it contains all the cell's relevant information. So the second big difference between a simple RNN cell and an LSTM cell are the gates. I mentioned the gates in the last slide, but now we'll discuss them in more detail. The main purpose of the gates are to filter out irrelevant information, so only the most relevant and useful information is left in the cell state. There are 3 gates, which we'll talk about in more detail in the following slides, but their names are the forget gate, the input gate, and the output gate. So you may be wondering, how do the gates know what information to keep and what to remove? It turns out the gates actually learn how to filter the information during the training process. The gates can be viewed as different layers in a neural network, which would be the LSTM cell. The gates can also be thought of as an entire neural network themselves. So the first gate that information in the LSTM passes through is known as the forget gate, and I've highlighted that gate in the image of the LSTM cell below. The main purpose of the forget gate is to decide which information from the previous cell state is irrelevant and should be dropped from the LSTM cell. If we follow the flow of the forget gate, we see in the bottom left that the previous hidden state, which is ht minus 1, and the current input, which is xt, those both get combined and then processed by a sigmoid function. And the result of that sigmoid function is going to be a vector of values between 0 and 1. 0 would mean drop the information, 1 would mean keep the information. We call that output the remember vector. Then following the sigmoid function, the remember vector gets multiplied against the previous cell state at the top. That begins the process of updating the cell state with relevant information. The second gate information must pass through in the LSTM cell is called the input gate. The main purpose of the input gate is to decide which information is relevant and should be retained and added to the current cell state. When we evaluate the input gate in the image shown below, we see the same inputs as the forget gate. That is the combination of the previous cell state, ht minus 1, and the current input, xt. This time, however, those inputs get processed by two separate activation functions. One is the sigmoid function, and the other is the hyperbolic tangent function. So these two activation functions produce two intermediate outputs. Those intermediate outputs then will get multiplied as signified by the x. The output from that is the gate output, which is known as the save vector. In the final step, the save vector gets added to the cell state, which again updates the cell state. The final LSTM gate is called the output gate. The main purpose of the output gate is to decide which information from the inputs as well as from the current cell state should be used for the current hidden state. As you may have guessed, the inputs for this gate are once again the previous hidden state and the current input. Those combined inputs are processed by a sigmoid function to produce an intermediate output, which is a vector of numbers between 0 and 1. At the same time, the current cell state gets processed by a hyperbolic tangent function to produce another intermediate output. These intermediate outputs then get multiplied together to produce the current cell state and the current hidden state. And as you know, the current hidden state gets fed back through the cell as the previous hidden state in the next iteration. For the next part of the project, I used an LSTM model to forecast a time series dataset of my choice. I chose to use a subset of the average temperature dataset that we reviewed in the first slide. Specifically, I wanted to forecast the average temperature for my home state of Louisiana from January of 2010 through September of 2013. The architecture of the initial model is drawn out in the image below. This network has 6 layers, 2 LSTM layers, a dropout layer following each LSTM layer, and a fully connected output layer. Each LSTM layer contained 20 neurons, and the dropout layer was set up with a dropout rate of 10% to help remove some of the bias from the model. The model was trained and tested on data from January of 1891 through December of 2009. Then I attempted to forecast the average temperature for the remaining 45 months. I just want to note that the data set containing the earlier temperatures I think I mentioned earlier that it has some blank values. It actually goes back to 1850 something, but I started at 1891 because there were no gaps in the data. So going back to the model, the length of the input series for this model was 30. So that means that we used the previous 30 data points to make a prediction. I trained the model in 10 epochs. The image on this slide shows the actual average temperatures for 2010 through 2013 versus the average temperatures that the model predicted. So when you look at these two images, these two waves, it looks like the model did pretty well. The average temperature, or the average error, appears to be about 4 degrees Celsius just from eyeballing the distance between the two waves. So the model's predictions definitely follow the actual numbers pretty closely, indicating that the model did successfully learn the relationship in the sequence data, the average temperatures. So next, we're going to see if we can try to improve upon what this initial model has done. For the final part of the project, I changed some of the parameters of the initial LSTM model to try and get better performance when forecasting the average monthly temperature for Louisiana. So if we walk through some of the parameter changes I did, one of the first ones is I added one additional layer, and you can see that in the model architecture diagram on the slide. That's one additional LSTM layer. I increased the number of LSTM cells in each LSTM layer from 20 to 50. So a little bit more than doubling the number of LSTM RNN cells. By creating a slightly more complex network, the hope was that the network would be able to learn, or to better learn, the relationship without overfitting. Along with the additional LSTM layer, I added another dropout layer as well. And with that, I also increased the dropout percentage from 10 to 20, hoping that that could eliminate even more bias from the model without having any negative effects. Another change I did was I increased the length of the input sequence, and I changed that from 30 to 60, so exactly doubled that. For this model, the preceding 60 data points will be used to make a prediction. And that's instead of the 30 data points that we were using in the initial model. 30 data points captures about 2.5 years, but with 60 data points, we're capturing about, I think, 5 years exactly. So using 5 years to predict the next month. So if there's any pattern in the average temperature that spans longer than 2.5 years, this model will hopefully pick up on that pattern and use it to make a better forecast. The final change I made was I increased the number of training epochs, and I increased that from 10 to 50. So this model took quite a bit longer to train than the initial model. On this slide, I compare the parameters of the initial model to the revised LSTM model so you can easily see what was changed. Again, I increased the number of layers, the number of LSTM neurons, the dropout percentage, the input sequence length, and also the training epochs. When we look at the two charts below, what we find is that these parameter changes appeared to have a positive impact on the model. That is to say, the changes improved the accuracy of the model's forecast. The chart on the left shows the forecast from the initial model compared to the actual average temperatures. The chart on the right shows the revised model's forecast compared to the actual average temperatures. When we compare the distance between the orange and blue lines for each of these graphs, we can see that the distance between the lines is noticeably less for the revised model versus the initial model. This indicates that the revised model had less forecasting error. Otherwise stated, the revised model performed better. Based on this result, I assume that the parameters could be slightly adjusted further in the same direction to improve the model's forecast even more. Before I end the presentation, I have a couple of closing comments and reflections I'd like to walk through. The first point is one thing that I learned from this project and experienced in this class is that LSTM models are much more stable than simple RNN models. And we know why. Simple RNNs are highly dependent on the random weights in the training process. And the sooner those weights approach zero, the sooner the model's performance will degrade. And that's called gradient descent, right? You can run the same simple RNN model 5 times and you can get 5 wildly different results. Thanks to the cell state and the gates, LSTM models don't depend entirely on those random weights, and because of that, we see fairly consistent performance as a result. Another thing I learned specifically from this project is that tweaking the model parameters can result in better performance. So it's important to test different parameter values and see how the model responds. Lastly, this course covered very fundamental concepts that I believe can be applied really broadly. Sequence data and sequence data sets, especially time series data, are very common, and with the knowledge I gained in this class, I'm excited to have another tool for solving problems involving this kind of data. Well, that concludes my presentation, and I want to thank you for your time and attention.